So when kappa is positive, and the right hand side of the ODE is going to be multiplied, it's going to be a constant multiplied, a positive constant multiplied by this matrix, which means the ODE is also going to have a set of eigenvalues. So, well, the ODE is also going to have a set of eigenvalues. Let me erase this one. That goes from 0 all the way to something that is minus something minus constant times delta x squared. And in fact, I think it's like minus 4 times kappa. Yeah, minus 4 times kappa divided by delta x squared. So what does that mean for our ODE integration schemes? So anybody recommend a scheme for me to solve these kind of equations? Huh? Not midpoint, exactly, right? Midpoint has a stability region over here. It doesn't even intersect. I mean, it intersects, but barely intersects with the eigenvalues, right? How about Forward-Euler? Yes, right? Forward-Euler is actually not a bad choice because Forward-Euler would have a stability region. Change my color a little bit. Forward-Euler would have a stability region like encompasses a whole circle, right? So Forward-Euler could actually encompass all the eigenvalues, which is what is needed for stability. Okay, and of course we know that Forward-Euler, the stability region depends on delta t. So, and the smaller delta t is, the more stable Forward-Euler is. In this case, how small would delta t have to be? How small would delta t have to be? Yeah, delta t basically has to be, this is minus 1 over delta t, right? So basically delta t has to be small enough so that it's on the same order as delta x squared, right? So the constant is not important, but like what we need to know is that we have to scale delta. Every time we make delta x smaller by a factor of 2, delta t has to be smaller by a factor of 4. All right. So this is actually something special to second order spatial derivatives. And if you ever encounter equations with even higher order derivatives, like a third order derivative, and some equations has fourth order derivatives, this problem is even worse because if you have a fourth order derivative, the delta t requirement, if you use any explicit time integration scheme, would be proportional to delta x to the fourth, right? So if you refine the spatial grid by a factor of 10, well, you have to take a time step that is 10,000 times smaller. So, yeah, it's known that if you have an equation with a high order spatial derivative and the coefficient on this high order spatial derivative is not negligible, you have an equation that is very, what's the adjective? Right. What's the adjective we learned that an equation that requires you to have extremely small time steps? Stiff, right. A high order spatial derivative is going to give you a very stiff equation to solve. So this is a stiff equation, right? Stiffness comes here when you have a kappa that is, I mean, if kappa is much smaller than A, you would be okay, right? But if kappa is not so small, then you have a problem. Therefore, in that case, the best scheme to use in that scenario is going to be an implicit scheme, right? If you have an implicit scheme like forward Euler, like backward Euler, your stability region encompasses the whole, essentially the whole negative real line. And then you can really take a time step that is unconstrained by stability. It's only constrained by accuracy, right? If I solve the equation, it's not accurate enough, I still have to decrease my delta t, but I'm not really constrained by stability concerns. All right. Okay, so this is what happens when you have a second order derivative. And one last thing is that at the end of the last lecture, we showed that when we have an equation that combines a first order derivative with a second order derivative, solving this, discretizing the first order derivative using a central scheme actually works much better, right, than solving an equation without kappa, without a second order derivative with a central scheme. Oh, the reason is also because of the eigenvalues. Even if you add a little bit of diffusion, right, second order derivative, the eigenvalues of a central difference scheme is no longer going to be lying strictly on the imaginary axis. Okay, actually lies, it shifts it a little bit towards the negative real axis. So you're going to be having a stable equation. Okay, so when you have a stable equation, of course, a second order spatial approximation scheme is going to win over a first order spatial discretization scheme if both are actually stable, right? The reason the second order scheme seems to be making roughly the same order of magnitude of error as the first order scheme is because the second order scheme is actually marginally stable. Okay, so that concludes our discussion on the second order spatial derivatives. We have basically introduced the partial differential equations. We have learned how to discretize the first order and second order derivatives, and studied how could different discretizations affect stability of finite difference.